Great. And well, so how do we got here? How do we go from 2019 to 2025 from my perspective, my journey through humanoid control? And since I just graduated, I kind of did a little bit of reflection of, okay, what are the things I was thinking about besides, want to publish another paper? So I think I was thinking about scaling up humanoid control, like just raw scaling it up to do more tasks. And that's where the universal comes in, like supporting different tasks and do different things. So the central question I was trying to answer is centered around three axes. The first one is complexity. I've been going from whole body control to whole body dexterity and then whole body visual dexterity. And then from single task to diverse tasks, and then from simulated to real world. So complexity grows, and we really want to get to this place where we are dealing with real humanoids, very complex visual tasks, and not just one task, but multiple tasks as well. So how do we get here? And I kind of have like a 3-step recipe that I've been following in scaling up humanoid control and then trying to make them useful. And here's the 3 steps. The first thing I did is get humanoids to learn to move like humans. So large-scale motion imitation or motion tracking. This is the first ever task that I was really gung-hoing, getting it to work, getting it to a semi-solved state. And the second is learn to explore like humans by learning control priors for reinforcement learning and for exploration. And then finally, dexterous and perceptive policy learning. And step 2 and 3 actually comes really well after step 1. And I will cover very, very quickly. Hopefully we'll fly through these papers from motion imitation, large scale, and in real world to learning control priors. And then finally, that's mostly in simulation, humanoid grasping and then perceptive policy learning. So let's jump right in. The first thing that I was really obsessed about for I think 3 or 4 years is scaling up motion imitation. The task of a motion imitation is translating kinematics to dynamics. So if we have a large-scale humanoid human motion data set, since we're doing humanoids, I said, okay, we want our humanoid to be able to do the exact same things, exact same motion that humans can do. And this is very challenging because humans can do many, many different things. You can walk around, jump, and cartwheel. So to scale up humanoid motion tracking, we kind of can see a progression between imitating single clips, this is 2018, and imitating, say, 8,000 motion clips. And with some help with magical forces, I was able to get to about 97% and 10,000 motion clips, a mass data set, the largest one in academia. And with large-scale physics-based simulation, I was able to get around 100% success rate on those. And gradually, there are some follow-ups that does terrains and scenes. But we can see a very clear progression of capabilities in terms of scaling to more motions, more environments, and much harder and harder tasks. With real humanoids as well, you can imitate maybe 10,000 motion clips with okay quality, but we want to iterate and make it more and more agile. And there was more recent work that imitating 8,000 motion clips with high quality. And we can kind of clearly see a scaling going forward with motion imitation. And I believe motion imitation will be a central task a proxy task to solve and get the motor skill capabilities to support, say, more interesting things like local manipulation. And in the interest of time, I'll just kind of give you guys a very quick overview of what motion imitation task is. The input is just reference motion, and the output is joint target goals, and reward is how well your policy matches the reference motion. Now, the only thing that I cared about the most in the motion imitation or motion tracking task is success rate, and that's kind of what set our work apart. Is that we're very focused on can you actually imitate all of these motion sequences with high success rate? If you cannot, then even if you are generating interesting behavior, that's not good enough. You have to successfully, within some margin, imitating full motion sequences. And that leads to a very severe forgetting problem where during training, the success rates start to zigzag. And we can call it catastrophic forgetting. We can call it network capacity, but it's a multifaceted issue that we have to solve to get to, say, imitating every single motion in the data set. And I can assure you, it can do the 97, the most simplest ones. The hard ones, the cartwheeling, the break dances, those ones are the difficult ones that the policy will struggle. And this is a fact I call policy learns to cartwheel, then forget to how to backflip. And if you listen to this talk during my thesis defense, I have a whole spiel that I worked through. Okay, we need to do this and do that. But since we're being honest in workshops, I'll give you guys the actual things that work, that are really good. So the central idea, there are two things that make this work. The first thing is progressively focus on harder and harder motion sequences. You don't have to do this motion primitive kind of thing always. But though there are papers that think MOEs are important and helpful, I'm sure they are. But so the two things that are important is, just progressively find harder and harder motion sequences to test on and just keep iterating on this process. And at some point, you will get your policy to learn every single one of the motion sequence. Trust me on this. I've tried numerous times when it not uses, the policy success rate will get stuck on 97%. But if you do this, you've got big GPUs trained for long enough, you'll get there. And the second thing is scaling your network. I know there are RL practitioners who keep telling me that, okay, we only need 3-layer MLPs. But just doing this task, I have seen clearly scaling in the network capacity is very simple. I did not believe it when I was doing it, but I did a 6-layer MLP and it worked. So I was educated. But we'll be able to get 100% success rates, low error, blah, blah, blah. It looks good. And I call this the perpetual humanoid controller, which kind of forms the backbone of almost everything I do from this point on, because it provides the motor skill capability. It let me know that my control system looks good, works well, and it was able to do some interesting things like getting up from the ground. And this is the first step I took to scale up. We have PHC, and the two important things are sampling schedule and larger networks. That's all you need to know. Don't need to read the papers. That's all you need to know for motion imitation. But it can only be applied to motion imitation tasks. It needs reference motion as input at all times, which is not really the best interface for solving manipulation. So the next thing I did is try to learn a generative control prior, such that we can sample good actions, human-like actions from a pre-learned latent space. So why is this important? Now, the issue I'm identifying here is, I believe every person who have trained RL humanoids this is very familiar. You have some zero pose, and your humanoid is like doing jittering around that pose and then flopping around. This is not how we explore. We do not just randomly flop around and then try to explore the scene. Not even small babies. Humans are preloaded with a sequence of pre-programmed motor skills, priors, whatever we want to call it. We see something shiny, smells good, we want to grasp it. So we are preloaded with these type of pre-programs that can be directly used to explore and then do interesting things. So how do we enable our humanoids to do that? How do we enable motor skill reuse? So very simple idea as well. So we have a space of all possible human joint torques. Obviously, exploring this space is going to be very, very expensive. And if we can explore in a human-like motor skill latent space, that would be fantastic. That means we're doing human-like things, doing our exploration, and I can guarantee you that it learns faster because now you don't have to spend, say, the first half of your training curves just to learn how to stand up. So how do we sample from this? And what has set this work apart is we're also scaling. So we're not just learning a small scale, previously learned latent space, for the animation. Most of them are just like have a small scale doing one task like locomotion or doing object interaction. But we want to like really recover this whole space. We want to scale up this motor latent space as well. And I do apologize. The latent space, control prior, motion representation, motor primitives, they all kind of mean similar things in this context. It's an overloaded term. I know, we know, but let's roll with that. So how do we form this control prior? The idea is very simple. We already have a great motion imitator. What it does is if you give me reference motion, an imitation goal, and give me proprioception, and at every frame I will compute a human-like, will compute an action that leads to human-like motion because it's imitating reference motion. So if we can form a distribution of the action distribution conditional on proprioception, we'll get this latent space, or we'll form a distribution that we can sample from to form human-like motion. And that's what I did. I trained a VAE where it does the same task as motion imitation, as an encoder, decoder prior, nothing special here. And in order to train this, we'll query the perpetual humanoid controller, the motion imitator, and query that for ground truth, pseudo ground truth actions, and we'll do distillation. This is not the only way to do this, but it turns out to be very effective. I like the structure. This is not the final product. I feel like we need better structure than this, but this was we were able to get a lot of the motor skills from the motion imitator through this formulation, and we call this pulse physics-based universal humanoid motion representation. And we use it. We freeze the prior and decoder, and we were able to apply this to other tasks, so downstream tasks as well. And yeah, just do hierarchical RL. Nothing special here. But I think this is the real important thing. If you use this latent space, you're starting to, when you're exploring, the humanoid is already standing up. It's doing interesting things. It's walking around. It's doing non-trivial things already. For tasks like reach and locomotion, you're learning it in like 100 steps. Compared to previously reinforcement learning based methods, you will get much better results and much faster convergence. And we apply it to a decent number of generative tasks. And I think the interesting thing are the last two ones, because when I train a motion imitation task, it doesn't have humanoid object interaction. But the motor skills learned there can be used for a terrain traversal task, which is difficult on its own. So we took one more step. We didn't really scale up on our capabilities, but we obtained a very good tool for learning downstream tasks like grasping and then visual grasping. So Pulse has generative capabilities, and you can random sample actions from it, as you can see during the exploration. But it's not interpretable. And it's a 3-stage pipeline. I'm very much looking forward to finding a 1 or 2-stage pipeline that can learn such a motor skill within space. And so equipped it with these two bad boys, let's now look at some actual useful and interesting tasks. So the first problem I want to tackle is, given an object and desired object trajectory, we like to control a simulated humanoid to grasp objects and follow desired trajectories. So input is 3D object and object shape, position, and then desired trajectory. It's a trajectory following task. This is difficult because I can assure you there's no motion capture that can generate or just give you a sequence of motion where the humanoid is grasping something and then following and tracing out the omnigrasp word in 3D space. So not enough data to train. That's why a lot of people have been working with just a disembodied hand just to grasp things. So, well, you're talking to me, which did PhD in Pulse, so I'm going to give you the solution I'm going to give you is, all right, let's first learn a motion imitation and motion tracker and get the motor skills we needed to perform these tasks. So we'll learn a PHCX, the motion imitator with fingers, and then we'll do PulseX, which is a control prior that has fingers. So we added a dexterity to our whole body motor skill prior. And we'll just train RL on top of this with magic states from simulation. If you talk to a vision guy, it's like, okay, where did you get these states? Where's the object? That's all from simulation. This is simulated. So magic vision, magic perception. And this is ground truth object state from simulation. And with this, we're able to train, simulated humanoid to grasp different objects. Interesting. And this is a results which I really like, is if you don't give the humanoid prior, this is kind of the thing you will learn because of the high degree of freedom. It will go absolutely crazy. So I have been asked why we're using human prior, why we're not using for humanoids, why we're not doing superhuman stuff. And my answer would be, well, we can't even do the human-like motions, and the human-like motions actually provide a somewhat constrained solution space that is near optimal, give or take. Now, what about vision? All the humanoids I've trained are blind, so what about what happens if we add vision into it? So, well, vision-based policy faces a sphere issue where you actually don't know where the object is. Like you need active perception. Also, specifying different goals is going to be challenging. To support a task like cleaning up the kitchen, you will need 1,000 different states. Well, maybe not 1,000, like 10 different states. Like this is going to be like 20 dimensionality. And this is not really scalable. What if we want to open the drawers now? So what we did first is we want to introduce a paradigm or reiterate a paradigm, and where we use perception, like in video games, you specify where the humanoid should go, what the humanoid should do, and you just tell it through perception only. And with this, I was very surprised that this actually worked, and just like specify which object to pick up through a mask, and then tell it when to pick up, when to put it down. And that all kind of worked with just perception. Perception is very redundant, so you can specify a lot of things with it. And unfortunately, we didn't really innovate too much on the algorithm side, so we just scaled it up, train with more GPUs, more cards, directly from vision. We didn't even do distillation. And we were able to get decent results with grasping different objects. And then we have some emergent capabilities like memory and grasping, and searching for the object. And we call it PDC, the Perceptive Dexterous Humanoid Controller. And I see that I have 3 minutes left, so I'm going to be very, very fast going through the rest of the slides. PDC, we have visual whole body dexterity, and the issue is this is just the start. This is just the start of this task. We're by no means solving this, even in simulation. So I recommend everyone to think about, even in simulation, if you only have perception, what do you do? How do you handle the active perception, learning from visual signals, etc.? What about real humanoids? We're back to square one, unfortunately. Real humanoids is much more difficult. Even though the learning-based humanoid controllers are making a splash, we're still in square one. Local manipulation is still very difficult, but we're very vastly approaching the capabilities. See if I can get this through this in 1 minute. Okay. We want to get PHC to the real humanoid. PHC sim to real. Problem one, retarget human motion to humanoid. Not easy. Still working on it. I hope the animation folks can pick up my slack. We need some great retargeting policies. So mapping from human motion from the MS data set to the humanoid, plus graduate student descent on finding the right policy, the right reward, tune it for 1,000 hours, and then cry about it, and then stay safe, hopefully. And we're able to do somewhat good policy, able to teleoperate, do interesting things, walk around. Don't laugh at it. It's our second real humanoid work. It walks a little awkward, and it's not agile enough. I would say it walks like a grandpa and moves, grasps things like a grandpa, just doing everything like a grandpa. Very slow, and this is one-time speed. And so follow up. What we're doing is say, okay, when we want to improve the agility of the policy, let's learn a real-world dynamics aligning function such that we can really approximate simulation with the real world. And with a bunch of jumbles and then many more hours of tuning, we're able to do these type of actions. And we call this ASAP, aligning simulation and real-world dynamics. Okay, the real stuff that I want to talk to you about. This is not important. Okay, I think scaling up motion tracking is important. It's not the final task, but it's a great proxy task to make sure that you have good motor control capability to support all of the things you want to do for your sim or your gameplay. Hierarchical RL and learning makes learning much easier, and I think that's the natural ways how we humans learn things. And vision and loop control still has a long way to go. We're just starting to see manipulation sim to real. If you're doing behavior cloning, ignore me. You guys' stuff work. Our stuff still needs a little bit more time. But vision and loop sim to real are still. We have come a long way, but we'll figure it out at some point. We should always figure out tasks in simulation first, and then apply them to real. I think that's a great way to make progress. And use what you build and build what you use. I build stuff. I did PHC, I did Pulse, and I keep using them, reusing them. Probably need an update, but I was able to get a lot of things out of them because when I built them, I was like, this is what I want to use. We're still far away from there, very far. How do we get there? This is my blueprint. Don't take me too seriously. But step one, let's learn a behavior foundation model with vision and loop. Maybe verify that in simulation, maybe be able to do all kinds of different things. Step two, let's just try to associate behavior with intent and language. And to step three, maybe real world learning and scaling. Very, very rough. All right, this is the interesting stuff that I want to get to. So here are some hotcakes. What has worked for humanoids? This is something that I've been reflecting for the last couple of days. PPO, unfortunately, I can assure you 90% of the work that you see on real humanoids are trained with PPO in Isaac Gym or Isaac Lab. Victor is here, so thanks to him introducing Isaac Gym to us. And reward tuning and graduate student descent, definitely the real MVP in this whole thing. And motion tracking a little bit. There's a bunch of them, that are working on this. And I will not list the things that are not working, but I assure you, everyone probably have something in their mind. Okay, that stuff probably didn't pan out. But these I have been constantly seeing are the things that have been working and been showing great results. And humanoid object interaction in physics simulation, I think is almost there. Still haven't seen a humanoid grasp a tennis racket and start playing and then actually play it well, but I'm sure there are people working on it, and within 1 or 2 years we'll see papers that does that. In a case-by-case setting, almost solved. Humanoid control in real world is fast approaching of being solved. This will, some people will say, I don't know, we're still very far, but some people say, it's solved, let's not work on that. So this is one of the hot takes. And so I believe now is probably a great time to work on behaviors. And this is just kind of what keeps me up at night. I don't think Sim2Real is going to get us there. So how do we learn in real world and then leverage the priors we have learned in simulation is important. Right, that's what I have. Thanks, everyone.
Great talk. You have time for your questions.
Yes.
All these questions. So there's the joint position there.
Yeah.
Add them up, and the control becomes
The 25 millimeter is average across whole body, globally. So it factors in everything. It's a global error. And yes, for end effector, it will be a problem. That's why I do not recommend doing pure motion imitation. Use a kinematic motion tracker, like a motion tracker, to do manipulation because of that 25 millimeter. That's huge in manipulation sense. You're a couple centimeters away. then you don't grasp the object. So yes, that's end effector definitely is a big issue. But this is the kind of the beauty of motion imitation task is you learn the motor skills to achieve like good end effector precision. But then in order to actually get that of performance, you probably need to re-leverage and relearn task and use these motor priors. Yeah.
Are there any work directly this point after like this motion that is part of soft laws for your joint after
Yeah. That definitely works. I mean, I have worked like Paul's actually showed like 3-point VR tracking. I think the end result's like 30 millimeter on average on the end effector. So 3 centimeters on average. I mean, when you're following, you can sometimes overshoot. So there definitely formulations like that. Basically, the idea for that is, okay, let's just do RL. Let RL figure out all the IK, all the whole body control for us. Definitely a valid solution. But then again, I feel like if you're going there, why not just directly learn the task directly? Because that's where you will actually get the precision you need. Like for example, for this grasping policy, I have to actually learn it with the object in the loop because tracking will miss the object for sure.
What do you see the difference between like control and behavior? That was part of your final slide.
Yeah. So control is being able to do something. Behavior is knowing what to do at certain situations. So the first step, I feel like for motion imitation, there's no goal, like high level semantic or goal per se. Just okay, I give you a reference sequence of motion. Now you do it. This task makes sure that you can move the way like I can. If I want to open doors, I want to first know that we can do this motion. Lean in and pull out and pulling and do things. Then behavior is knowing you need to do these when you see a door. So I think it goes hand to hand. Once you have the control capability, which is being solved, and then you start doing, okay, more semantic, in context, what do you need to do to solve these tasks? So that's behavior.
Maybe I have one more question.
Mhm.
In terms of like those, if there's additional challenge, let's say if I was managing the real app solves all the time.
Absolutely. That's why I'm on the camp of control is not solved. It's not even close. But there is, for RL there, you can learn very robust policies. Someone will say you will never fall, but obviously that's all a relative. I think like being able for the controller of being able to predict its own actions of what will happen is important, and letting the controller know that's something that it cannot do. Because, for example, for the motion imitator I developed, the policy doesn't know that it cannot do some action. So if you just feed the reference motion to it, it will try to do it and fall down. Maybe it'll get up, but it doesn't actually know that it cannot do this sequence. So how do we get a policy to say, I refuse? I'm not going to do that because this is dangerous. I mean, you can have some ways of doing that, but I feel like that's we want. I'm looking for some more elegant solutions. I mean, technically, you can just do some switching. So if I think I can't do it, I just switch it to a different policy. But yeah, I think that's something that we should look into.
Okay, time that's sent the speaker there.
Thanks, everyone.